Chapter 4 project by Anita, me, and my partners Donovan and Fabio. Lesson 4.1 Chemical Bonds and Greenhouse Gases. This lesson just talked about how greenhouse gases are transparent to visible radiation, which allows sunlight to pass through. However, greenhouse gases are with carbon dioxide, and carbon dioxide gets trapped in Earth's atmosphere, where we have global warming and climate change because of the carbon dioxide trapped in the atmosphere. Another thing I learned about is the ionic bonds and how ionic bonds consist of cations formed from metallic elements and anions formed nonmetals, and this is all held together by a electrostatic attraction between the ions of opposite charges. And basically this lesson just talked about the basics, and yeah.
Now onto electronegativity, unequal sharing, and polar bonds. First off, what are covalent bonds? A covalent bond is a chemical bond that involves the sharing of electron pairs between two atoms. These electron pairs are known as shared pairs or bonding pairs. The stable balance of attractive and repulsive forces between the two atoms when they share electrons is known as covalent bonding. There are two types of covalent bonds: polar covalent bonds and nonpolar covalent bonds. A polar covalent bond is a bond in which the electronegativity difference between the atoms is between 0.4 and 1.7. In a polar covalent bond, pairs of electrons are unequally shared between two atoms. In the bottom left image displaying the polar bonds in a water molecule, it can be seen that the pairs of shared electrons spend more time with the oxygen atom. Because of this, one end of the molecule has a slightly negative charge and the other a slightly positive charge. However, in a nonpolar covalent bond, the pairs of electrons are shared equally between the two atoms. Therefore, the number of electrons shared by the adjacent atoms will be the same. Also, the difference in electronegativity of nonpolar covalent bonds is negligible. Onto electronegativity. In 1932, American chemist Linus Pauling proposed the concept of electronegativity to explain the polarity of certain covalent bonds. Electronegativity is an atom's tendency to attract electrons towards itself with a chemical bond. The higher the electronegativity, the greater an atom's attraction for electrons would be. The lower the electronegativity, the lesser an atom's attraction for electrons would be. Typically, the electronegativity of elements increases across a period from left to right and when moving up a group. The attraction that a bonding pair of electrons feels for a particular nucleus depends on the number of protons in the nucleus and the distance from the nucleus, which is what would explain the trend we see on the periodic table.
Let's go ahead and move on to naming compounds and writing formulas. So first we're going to start by naming binary molecular compounds, which are just two bonded nonmetals. So first we're going to write down the name of the first element in the chemical formula. Then we're going to write down the second element and change the ending to "-ide". We also have to add prefixes to the elements based on the number of atoms in the respective chemical formula. Another rule is to remove the prefix ending O or A if the element starts with a vowel. Also, if the first element only has one atom, then you don't have to add the prefix mono to it. Let's go ahead and move on to some examples. Let's say we have SO4 and we're trying to derive the compound name. So we see the first element is sulfur, so we go ahead and write that down. And the second element is oxygen, and it has 4 atoms. That means it has to have the prefix tetra. We have to change the ending to "-ide since it's the second name, element name, and our compound name. And that gives us sulfur tetraoxide. We can also work the other way around. Let's say we start with diphosphorus pentoxide. So we can see the first element is phosphorus and it has the prefix di, so we know there's 2 phosphorus atoms. Then for oxygen, it has the prefix pentose, so we know there's 5 oxygen atoms. And that gives us the chemical formula P2O5. Let's go ahead and move on to binary ionic compounds. So first step to writing their names is to write down the cation name first, and you just have to write the parent element name. Then you're going to follow it up with the anion and change the parent name ending to "-ide". No prefixes are used because the amount of atoms is implicated by their charge. A major exception is with transition metals, since sometimes certain transition metals have multiple charges. To differentiate between the different versions of a transition metal, we use a Roman numeral after the metal to express the charge on the cation. Also note that this does not apply to all transition metals, since some transition metals are only present with one charge. Let's go ahead and skip to the third example. As you can see, we're dealing with iron, which can either have a +2 charge or a +3 charge. So to differentiate between both in our compound, we go ahead and add the Roman numeral 3 to our formula name. As you can also see, there are no prefixes because iron has a +3 charge, so there has to be 2 iron atoms and 3 oxygen atoms, which have -2 charges, to cancel out and give us a neutral compound. And let's go ahead and move on to naming polyatomic ions. So polyatomic ions are covalent bonds of 2 or more atoms, and they have a charge since they're ions. Most polyatomic ions are oxoanions, which contain oxygen and 1 or more different elements. Usually for oxoanions, the ion name is the first element in the formula, which ends in I or A depending on the oxygen atoms bonded to the element. If it's a version with less oxygen atoms, then it ends in I, and if it's a version with more, then it ends in 8. In cases where an element has more than 2 oxoanions, there's 2 more rules. With the first being that the oxoanion with the most oxygen atoms starts with pre and ends in 8, and that the oxoanion with the least oxygen atoms starts with hypo and ends in ite. For naming binary acids, we start by adding hydro to the second element in the formula. Then we replace the last syllable with the second element's name with IC. We also add acid to the end. For oxoacids, we use the corresponding oxoanion name, and if it ends with A, then we change the ending to IC, and if it ends with I, we use the suffix OUS. That about sums up naming compounds and writing formulas.
Lesson 4.4, Lewis symbols and Lewis structures. This lesson basically just talked about Lewis structures overall, and it even taught us how to draw Lewis structures. So the 5 steps to drawing a Lewis structure. The first step would be to determine the total number of valence electrons. The second step is to arrange the symbols of the elements to show how their atoms are bonded, which is known as a skeletal structure, and then you connect them with a single bond. And actually towards another lesson we learn more about double bonds, but yeah, okay. So then you have to complete the ostet of all the atoms bonded to the central atom by adding ion pairs of electrons, and then you compare the number of valence electrons in the Lewis structure with the number determined in step 1, so the total number of valence electrons, and you complete the ostet on the central atom, and you have to make sure that they're all basically connected to the central atom because it's the central one. Yeah.
Now we will discuss resonance. When there are multiple different molecular forms of the same element, they are called allotropes. One example is ozone, an allotrope of oxygen. The energy found in lightning strikes contain enough energy to break oxygen to oxygen double bonds. The oxygen atoms formed from the strike then collide with O2 molecules and form ozone. Despite O2 and O3, ozone, both being made from oxygen, their properties are vastly different. Whereas O2 is a gas that is an essential component to life on Earth, O3 is a lethal toxic gas and when at ground level, is a harmful air pollutant. Now when the Lewis structure of ozone is produced, a double bond can be produced either with the leftmost oxygen atom or the rightmost oxygen atom. Well, which Lewis structure is correct? Technically neither. The possibility of having 2 Lewis structures for ozone introduces the idea of resonance. What is resonance? Well, resonance occurs when multiple Lewis structures are existent, as was seen with ozone. These resonance structures still have the same arrangement of atoms, but they just have different arrangements of bonding electrons and lone pairs. When resonance structures are displayed, a double-headed arrow will link the different resonance structures of a compound, as seen in the image in the bottom left. Neither of the structures are technically correct, however. The actual bonding in ozone is an average of the 2 resonance structures. The third bonding pair is spread across the 3 atoms. When this happens, this is known as delocalization of electrons. A molecule or ion with delocalized electrons is represented by several resonance structures. Here are the rules for resonance. Resonance structures should have the same number of electrons. Each resonance structure must follow the rules of Lewis structures. When writing resonance, only electrons can move, so the skeleton of the structure cannot be altered. And lastly, resonance structures must have the same number of lone pairs.
Alright, so the length and strength of covalent bonds. So first, let's start with the lengths. So the lengths of covalent bonds are dependent on 2 factors, with the factors being the atom's respective elements and the bonding order, which is the number of bonds, whether it's single bonds, double bonds, or triple bonds. So the smaller the atoms, the smaller the bonds. And this is usually the case. And the greater the bonding order, the shorter the bond length. This is because as the bond order increases, the amount of electrons being shared increases as well. So the atoms are forced to come closer together. Also, the lengths of bonds between the same atoms are about the same, but they still vary slightly across different compounds. So we can see an example in the bottom of the slide at the left of oxygen to oxygen bonds. So for the double bond, the bond is going to be smaller than with a single bond because, again, the atoms have to get closer to share those electrons. All right, so let's go ahead and move on to bond energy or strength. So the bond energy is the energy needed to break the bonds between atoms. And this is always going to be positive because the atoms like to be bonded. Together they can fulfill each other's electron needs, so you're always going to have to input energy into the system to break a bond. Also take a note that this is equal to the energy released when the bond is created. Again, this varies slightly across compounds when it involves the same atoms, the bonds of the same atoms. And as opposed to the lengths, the bond energy actually increases as the bond order increases. And this makes sense because more electrons are being shared, so the attraction between the atoms or the nuclei and the shared electrons is going to be much greater. We have some more examples of oxygen to oxygen bonds and carbon to carbon bonds. So the double bond in the oxygen to oxygen bond is going to have more bond energy than if it were a single bond because, again, more electrons are being shared, so the attraction is greater between the nuclei and the negatively charged electrons. And the same applies with the carbon to carbon triple bond and the double bond. In the triple bond, the positively charged nuclei is going to have a stronger attraction to electrons than in the counterpart double bond.
Lesson 4.7, Formal charge, choosing among Lewis structures. Okay, so in this lesson, I learned about what formal charge is, and I learned how to calculate the formal charge. So a formal charge is not a real charge, but rather an accounting system for the number of electrons that are formally assigned to an atom in a structure of a molecule or a polyatomic ion. So to calculate the formal charge, this first step would be to determine the number of valence electrons in the free atom, and then you count the ion pair electrons on the atom in the structure. You count the electrons in the bonds to the atoms and divide that number by 2, and you sum the results of steps 2 and 3 and subtract that sum from the number determined in step 1. This is going to just assume that each atom is formally assigned to its lone pair electrons and half the electrons shared in the bonding pair. And yeah, that's how you find the formal charge.
Now on to exceptions to the octet rule. First, let's recap on what the octet rule is. The octet rule is a general rule that states that main group elements have the tendency to bond in a way that results in each atom having 8 electrons in its valence shell. However, although the octet rule is generally applicable, the rule still has some exceptions. One exception to the octet rule is a molecule with an odd number of electrons. When a molecule has an odd number of electrons, it must disobey the octet rule. When there's an odd number of electrons, then there will be an unpaired electron in the molecule. As seen in the image near the bottom left, nitrogen has 5 valence electrons. When it bonds with oxygen, nitrogen will be left with an unpaired electron. This unpaired valence electron is known as a free radical. Another exception to the octet rule is the presence of an atom with too many valence electrons. When a molecule has one or more main group elements that carry more than 8 valence electrons, that element is hypervalent. In the middle image, the central phosphorus atom in phosphorus pentachloride can have 10 total valence electrons. One last example is ICO4 anion. In this ion, iodine actually has 12 total valence electrons.
Now let's discuss vibrating bonds and the greenhouse effect. So structures, the Lewis structure and other diagrams of atoms tend to implicate that the bonds are rigid, but they actually vibrate like springs. Specifically, in polar bonds, the partial separations of charges create small fluctuating electrical fields that vibrate at certain frequencies. Coincidentally, these frequencies match with the frequencies of infrared radiation from sources like the sun, and this could lead to photon absorption, like in the case of CO2, a greenhouse gas. When photons are absorbed, the electrons within the compound and the atoms are excited and they move on to higher energy levels or higher orbitals, and when they go back down to the ground state, they release energy back as heat, and this process is known as greenhouse effect. There are 3 modes of vibrations, and I'll be applying them to CO2 since it's a more common greenhouse gas. The first mode of vibration is the symmetric stretch, and this describes when polar bonds both stretch or both compress simultaneously. No photons are absorbed since the fluctuating electrical fields cancel out, and this is known as infrared inactive because it does not absorb infrared radiation. Second mode of vibration is asymmetric stretch, and this is when one polar bond stretches while the other compresses, or vice versa. This may cause photon absorption because the small electrical fields aren't canceling out each other. So if the frequencies match the exact frequencies of the infrared radiation, then it has a chance of absorbing the radiation. This is known as infrared active because it has the possibility of absorbing the radiation if the frequencies match. For the third mode, we have the bending mode, and this describes when the central atom moves up or down while the other atoms move the opposite direction. This may also cause photon absorption because the small fluctuating electrical fields aren't cancelled out, and this is also infrared active because photons may be absorbed. Thank you for taking your time to listen to our presentation.